Good morning, dear students. Today we are going to start with new chapter, that is permutation and combinations, and there will be three things in this chapter. And first one is fundamental principle of counting. We have I have written over here, and next is permutation. Then we will go to combination. So let us start today's class. That is fundamental principle of counting or multiplication principle. So what basically we are doing here is, if an event can occur in ways m different ways, and following which another event can be occur in n different ways, then the total number of occurrence of the event in the given order is m cross n, that is m multiplied by n. So basically what we are doing is, if there are two events and after occurrence of m, n is occurring, therefore what we are doing is we are simply multiplying m by n. We can generalize it. If there are three events followed by let us say p, then mn into p will be there. If there are three events m and followed by n and again followed by p, let us say, then there will be multiplication in the between these three, and our answer will be m cross n cross p, that is m into m multiplied by n multiplied by p. So we can generalize it. There can be as many as events can be there, and we can multiply all those events. So let us have example over here. Let us There are three pants and two shirts are there, and there will be a combination we will see. And not combination, actually we will calculate the how many possibilities are there to make arrangements over there. So let us consider there will be three pants over there and two shirts I have. So if I consider pant 1 and shirt 1, I'll get this as one of my possibility. And if I consider again P1 with S2, that is shirt 2, then this is my possibility. I'll wear this one. If I consider P2, that is pant 2 with shirt 1, then I'll get this one as my possibility. And if I consider that P2S2, this is my possibility. And if I consider P3, that is pant 3 with shirt 1 and shirt 2, I'll get this as my arrangement, or possibility is that much. So there are six possibilities or arrangement I have, which I can wear these three pant and two shirts. Let us have one more example. That is, let us say the word is rose, and I have to arrange rose without uh, without looking into the meaning over there. I have to arrange the word, and the letters should not repeat. So I can arrange any one word I can pick and I can put over here. So I can pick R also, O also, S and E. There are four options I have over here. If I put R over there, then there will be remaining three letters are there. So I can put three letters over here. Then remaining portion what I have is only two. So therefore I can put any one letter out of these two letters remaining. So there will be two, and here definitely the last one that will come, that is 1. So by multiplication principle, if there are four events going on, R O S E, so what we are doing is followed by one it is following. So therefore multiplication principle we can use 4 into 3 into 2 into 1, therefore it will be 24. Now let us have one more example, that is two digit even number we want, and what we are doing is we are using 1 2 3 4 5. There are 5 digits are there, and again one more condition is there that the digits are repeating. So to get even number, what we need is in the unit place, in this unit place there are two places I have made 2-digit even number. Then unit place I need 2 or 4. That is mandatory for me to make this number as even number. Then it is repeating, and also 2 or 4, that means can be done in two ways. Either 2 can be here or 4 can be here, that is fixed. So there will be two ways. And again, because of it is repeating, it might be 1 or 2 or 3 or 4 or 5. So in all the way, what I am having is I am having the even number. So I am having over here 5 ways to put from 1 to 5 over here. So in 5 ways I can put in the tens place, and in units place I have 2 ways to put. So by multiplication principle I can directly write 5 into 2 equal to 10. That is the arrangement. 10 arrangement we can make from these digits to make 2-digit even number. Now you will be able to solve exercise 7.1, and we'll move further. And now in permutation, before starting permutation, we will discuss about factorial notations, and that is written in the symbolically in this form, that exclamation mark is there, and we'll not read that as exclamation, but we'll read that as factorial. So this is nothing but the product of first and natural number. First and natural number, the product we are finding out. That means if we want to write 1 into 2 into 3 into 4 into 5 into and so on up to into n. So these many things are equal to n factorial we have written over here. For and one more thing, we'll see this one, that is 1 factorial is nothing but equal to 1 only. 2 factorial is nothing but 2 into 1, and 3 factorial is 3 into 2 into 1. 4 factorial is 4 into 3 into 1 2 into 1. And what we are doing is I have written over here in the starting from 1. So it looks like in this situation. But the thing is, whenever we are calculating in our to solve the problems, what we are doing is we are writing from this side, that reverse side. Later on in the question we will solve in that manner only, and so on. We will write it over here factorial 5, factorial 6, 7, 8, 9, 10, everything. And one more thing, this is a very important thing, 0 factorial. This is read as 0 factorial or factorial 0, n factorial or factorial n. This is read as n factorial or factorial n. So this is 0 factorial. So 0 factorial is equal to 1. One should remember this thing. This is very important one. We will prove that also in later on. But one should remember that 0 factorial is 1. Now we will see the example how to solve the question. Question asks 5 factorial. So it's simply 1 into 2 into 3 into 4 into 5. So if we multiply 1 into 2, that is 2. 2 into 3 is 6. 6 into 4 is 24. And 24 into 5 is 120. So likewise we have calculated 7 factorial is nothing but 1 into 2 into 3 into 4 into 5 into 6 into 7, and that is equal to 5040. And if we need to subtract these two, 7 factorial minus 5 factorial, so we have calculated the value over here, this one and this one, so directly we can subtract over here. If we don't have these values, let us say if one can ask you directly 7 factorial minus 5 factorial, then you should first calculate the 7 factorial. Likewise this one, whatever I have calculated above, and after that you have to calculate 5 factorial like this. and you should write this value over here and you can subtract over here. Now the next question is compute 8 factorial divided by 6 factorial into 2 factorial. This is the question. So we can write 8 factorial as 8 into 7 into 6 into and so on up to 1 we can write. So what I have done is 8 into 7 and I have written over here as a 6 factorial. We can write the 6 factorial. If we multiply 7 over there in 6 factorial, it will become 7 factorial. If we multiply 8 to this particular 7 factorial, so it will become 8 factorial. And if we write, if we multiply 9 to 8 factorial, it will become 9 factorial. So likewise it is there. So what I have done is I have written over here 8 into 7 into 6 factorial. 6 factorial and 6 factorial will cancel out, and what I have is 8 into 2. Then this is 2 factorial. I have expanded it. Then 2 into 1. So 2 and 8 will get cancelled and I have 4 over there. So 4 into 7, that is 28. This is our answer. Likewise, this is very easy topic, and exercise 7.2 is based on this notation only. So you can solve exercise 7.2. Now coming to the second point, that is all the objects are distinct. So if there are so many events and nothing is repeating, so we can derive some formulas over there, and also we will have some more theorem over there. So theorem 1 states that the number of permutations of n different objects taken r at a time when or where r is between 0 to n and objects do not repeat is straight away given in the theorem that is equal to n into n minus 1 into n minus 2. It will go up to n minus r plus 1, which is denoted by NPR. This is denoted by NPR. So let us see there are so many vacant places are there. Say r vacant places are there, and total number of events we have is, or total number of permutation we have is of n objects, n different objects. I'll consider that as object or event. Both are the same thing. So what we have is n different object we have, and what we are finding is the permutation. So there are r vacant places, so many places are there. So I'll put first, what I have is I have an option of n different object I can put over here. Then I can put n minus 1 different object over here. Here I can put it n minus 2. Why it is n minus 1, n minus 2 is I have already put there as n different object. I choose one object and I put it here. So the remaining thing is this is filled, and these are r minus 1. So many vacant places are there, and I have object also as n minus 1 object I have. So there are so many options I have is n minus 1 options I have to fill this box. So I'll fill one more thing, that is n minus 1 trial I have, and I'll put it here. And after that, after putting over there, 2 objects are over, and I have n objects. So minus 2 if I'll put, then I'll get so many vacant places, and I can put this as over here. So likewise I'll put over here, and the last, that is rth vacant place I can put n minus r minus 1. So it will become n minus r plus 1 over here. So in r vacant places I can put n different object in these many situation or this many times. So by multiplication principle or fundamental principle of counting, I have to multiply all those numbers over there or objects so that I'll get my answer. So this is NPR, and derivation of formula NPR, we'll see that NPR is n factorial divided by n minus r factorial, and where r is between 0 to n, where 0 and n both are included. So first of all, NPR is nothing but, we have seen this is multiplied just n into n minus 1 into n minus 2 up to, it will go up to n minus r plus 1. This is nothing but equal to NPR, we have seen over here. So that's why I have not written. So what we are doing is multiply numerator and denominator by n minus r into n minus r minus 1 and so on up to 3 to 1. And numerator and denominator, if we multiply this, it will become like this. So we have already this much thing. Now I have multiplied n minus r minus 1 into and so on up to 3 into 2 into 1. So this is numerator part, and this is the same thing I have multiplied in denominator part also. So now it will be fulfilling its criteria from n into n minus 1, n minus 2 and so on up to 3 to 1. So it will become, n natural number is there. So now it will become n factorial, and here it is n minus r minus 1. So it is decreasing, and it will decrease up to 3 into 2 into 1. So now it will become n minus r factorial, and obviously r is, we can put the value of r from 0 to n, any natural number we can put there, so that we'll get the value of that. So it is very easy. I have taken one example, that is compute 6p2. It is read as 6p2, that there are 6 objects are there, and we are choosing 2 at a time, and we are going to calculate this. So 6 factorial divided by 6 minus 2 factorial, according to the formula, this is the formula we have, n factorial divided by n minus r factorial. So we are applying that formula over here. So 6 factorial divided by 6 minus 2 factorial, it is 6 factorial divided by 4 factorial. So I can write over there 6 into 5 into 4 factorial, and 4 factorial gets cancelled out, and 6 into 5, that is 30, our answer. Theorem 2, that is the number of permutations of n different objects taken r at a time, where repetition is allowed. Repetition is allowed, that is nothing but n power r. So if we have 6p3, definitely we will be having 6 factorial but divided by 3 factorial. This is nothing but 6 into 5 into 4, this is nothing but 120. So this is whatever I have written over here. This is nothing but the permutation where repetition is not allowed, but it is allowed. Then this should be, it is like 6 power 3. So now it will become 6 into 6 into 6. Likewise, you can calculate it. The theorem states that if repetition is allowed and out of n different objects we are taking r at a time, then its value is n power r. Now moving to the point number 4, that is when all objects are or are not distinct object. That means you will be having some repetition over there. Like let us say there is one word called root, and in this word, if we want to find out the arrangement, then we have factorial 4 divided by factorial 2, it will give us 12. So we will see how we can arrange it in 12 ways. So let us consider there are two O's. So I am considering one as O1 and another one is as O2. So whether I will write ROOT, that is O1 or O2, or if I want to write ROOT, that is whether that is R O2 O1 T. So both are the same thing, as we know that these two letters are the same. Therefore, I can write root over there. Similarly, TOOR, if I write, or TOOR, whether O first one is coming first or whether second one is coming first in order or in arrangement, that doesn't make any difference, and we'll get TOOR. Likewise, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So 12 arrangement we have, and we have seen this. You can pause this video and you can refer and read one by one how I have managed these all words. So let us move to the next thing, that is theorem number 3. It states that the number of permutations of n objects where p objects are the same kind and rest are all different, then we can write that is equal to the arrangement or permutation can be written as n factorial divided by p factorial. That means if we have four objects over there, and out of these 4 objects, 2 objects, these OO, are of same kind, that is of same kind. So n factorial, that is number of objects, we have 4, so we have written over here 4 factorial, and the p objects are of same kind, means there are 2 objects I can see which are of same kind, so I have written over 2 factorial. So this is the theorem number 3, and we can generalize it, we can, and after generalizing we can say the number of permutation of n objects where p1 objects are of same kind, p2 of second kind, so on, and pk of kth kind, means you are having so many different objects, and of that you have more than one object that is of same kind. So it is saying that if that is the situation, then factorial n, that is the total number of objects you have, and if that are repeating, then what you are doing is you have to just divide by that factorial, that is p1 factorial, p2 factorial, p3 factorial up to pk factorial. We'll solve some question over there so that you will get this concept. Now we have the word as daughter, and we have to arrange all the letters over there, and we have to find out the permutation, obviously, and there are 2 conditions. First one is all the vowels occur together, and another one is all vowels do not occur together. So what we are doing is there are 8 different letters in the word daughter, so 8 different letters are there. So what we are doing, and in that too vowels are A, U, E. So what we are doing is we are considering these A, U, E as one single unit. So now it will become as D, G, H, T, R, and this is one unit. So 1, 2, 3, 4, 5, and this is 6. So I can assume that as a 6 object, and in 6 object I can write the permutation as a 6 factorial, whereas AUE, this also will change its position internally. So there will be 3 factorial as there are 3 letters. So 6 factorial into 3 factorial will give us 4320 as our answer. And one more thing, the second one, the all vowels do not occur together. So we have find out that these many arrangements are there which represent the occurrence of A, U, E together. So we will minus these many arrangements from the entire arrangement. So therefore we will get that all the vowel that they are not occurring together. So 8 factorial, there are 8 letters, different letters. So 8 factorial will be the arrangement, and minus 6 factorial into 3 factorial. We have seen this, and it's better to take common rather doing multiplication, or I'll suggest you to use Bodmer's rule. It's better, and take common 6 factorial from the both the term. You will be having 8 into 7 minus 6 factorial, 3 factorial is 6, and again you can take common 2 from these two terms. So it will become 6 factorial into 2. Now it will become 7 into 4 minus 3. Now it is 28, this is 3, it will become 25, 25 into 2 will give you 50, 50 into 6 factorial, that is 720. So after multiplying you will get 36000. So these are the situation where you can have arrangements. Now we will consider the word institute. Here we will be having I as 2. Two I's are there here, and T, this is T, and this is T, this is T. So three times we are having T and I as 2 times. So these are of same kind. So total number of letters are total 9. We have calculated these are 9 letters we have, and out of that 9 letters, 5 letters that is of 2 of I and 3 are of T are the same kind. So permutation can be given as 9 factorial divided by 2 factorial into 3 factorial. Similarly, Allahabad, this is the word, and we have to arrange Allahabad. There are total 9 letters or objects we have, and out of that A, this is coming 4 times. 1, 2, 3, 4. 4 times A is coming, and L, this is 2 times it is coming. The rest are the different letters. So permutation can be given as 9 factorial divided by 4 factorials. A is coming 4 times, and 2 factorial as L is coming 2 times. So this is equal to 7560. You can calculate it very easily. So you can solve here, say exercise 7.1, exercise 7.2, exercise 7.3. You can solve and